Drift is only one of two major charge transport mechanisms that we have to understand if we are to understand how electronic devices work. The second mechanism of charge transport is diffusion. Diffusion is a natural process where a high concentration of particles in a container will start to spread out through the container until we reach a state in which there is an even concentration through the whole container. This is the process through which tea infuses water. It is the process through which a gas expands to occupy the container. It is a natural process and it affects electrons and holes as much as it affects gases and tea. So if we imagine that for some reason we had a high concentration of electrons on one side of the material, this will cause electrons to move to the other side and expand until they achieve an even concentration. If electrons are moving, this means that current is flowing. So diffusion can cause something called diffusion current, and it is important to understand diffusion current because it will be critical to understanding current flow in electronic devices, specifically in the p-n junction. So how do we calculate Jn, diffusion current density for electrons? It's obviously going to be proportional to dn by dx, where dn by dx is the gradient of electron distribution along the x direction. The steeper the gradient, the more diffusion current. The shallower the gradient, the less diffusion current. If there's no gradient, meaning that electrons are distributed evenly throughout the material, there will be zero diffusion current. And of course, it's going to be proportional to Q, which is the charge of a single electron. So there's a Q here. And there's a constant of proportionality. It's called the diffusivity of electrons, and it's given the symbol dn. And diffusivity just expresses how easy it is for electrons to diffuse through the crystal in which they exist, which is in this case a silicon crystal. Now, this means that when we look at electron current in a material, it's going to consist of two components. It's going to consist of a drift component and a diffusion component. And the drift component is going to be Q mu n n e, and the drift component is dn q dn by dx. Similarly, the whole current is going to be Q mu p times E minus dp q dp by dx. Now, we already noticed that the drift current for electrons and holes are going to be in the same direction, both in the direction of the electric field. Also, diffusion current for electrons is going to have the same sign as the drift current for electrons. But diffusion current for holes is going to have a negative sign, and we have to understand why that is so. So let's assume that the distribution of hole concentration looks something like this. Now this means that dp by dx, the slope of the curve, is positive at all values. So it means that this is positive. What this is going to do is it's going to cause holes to diffuse from the right to the left. They're going to diffuse from the high concentration to the low concentration. And this will cause a whole diffusion current Jp from the right to the left. However, if the electric field is positive in this direction, then the drift of holes is going to be in the same direction of the electric field and in the opposite direction of diffusion. So if you substitute for everything with the correct sign, the electric field correct sign, the gradient of hole concentration with the correct sign, you will end up with an equation that sorts itself out. Same applies for electron concentration. If we had an electron concentration that looked like this, then the drift of electrons would be in this direction. But if the electric field was positive, then electrons would also drift in the opposite direction, and so the drift and diffusion components of electron current have to add up. Now, if we look at the diffusivity constant, dn and dp, these represent how easy it is for electrons and holes to flow through the material. But what do mu n and mu p represent? they represent how easy it is for electrons and holes to flow through the material. So in fact, diffusivity and mobility are expressing the same thing, but they're just expressing it for two related phenomena, right? Diffusion and drift are different phenomena, but they are both phenomena in which charge carriers are trying to move in a crystal. And so diffusivity and mobility are related. And we have to find out how related are they. Is there a constant of proportionality somehow, and does it make sense? So to do this, we will consider a piece of silicon. And this piece of silicon has differential doping. So it's going to look something like this. And the Fermi level is going to be flat. So what this means is that the Fermi level is farther away from the valence band edge on this side than it is on this side. So it means that there are more holes on this side than on this side. Because there are more holes on this side than on this side, there will be diffusion. And similarly, there will be a diffusion of electrons from this side to this side. Now we are going to attach a short circuit to this piece of silicon so that there is no external field imposed upon it. So there is no external voltage source imposed upon it, and thus there is no net current flowing out of it. If we don't have an external voltage source, we don't have a net current. This doesn't mean, however, that there are no internal current components. There could be a diffusion current and a drift current as long as they cancel each other out. And in fact, we know that there is a diffusion current in this case because there is a gradient that we just saw in the concentration of holes and electrons on both sides. So let's write, for example, the electron current. Let's just assume that hole current is negligible in this piece of material. And so the total hole current is Q mu n, Ne, plus dN Q dN by dx. And this current is going to be equal to 0. So basically, we're going to have 0 net current flow, and we can cancel out the Q's. And let's just ignore signs for now and say that mu n times Ne as an absolute value is equal to dN times dN over dx as an absolute value. So as absolute values, they are equal to each other, right? Now, we have an expression for n, the concentration of electrons, which is Nc e to the power of minus Ec minus Ef over kT. We can differentiate dN by dx to obtain this term so that we can substitute it and see if it gives us anything meaningful. So we're going to get minus Nc over kT into e power minus Ec minus Ef over kT, and then we have to extend the differentiation because we don't know if Ec and Ef are functions of x or not, and so this is going to be dEc by dx minus dEf by dx. So if we look here, we find that the Fermi level is constant throughout the material. We will shortly understand that the Fermi level being constant in the material is a direct consequence of there not being an external voltage source. This is a state called thermal equilibrium, in which the material has no external fields applied to it. It doesn't see any sudden changes in temperature or light, and everything is in a steady state. In such a situation, the Fermi level has to be constant throughout the material. And so dEf by dx is going to be 0, and we can remove this term. And therefore, dN by dx, we notice that this whole thing is n, and so it's going to be minus n over kT multiplied by dEc by dx. But what is dEc by dx? It is the rate of change of the conduction band edge, which is also the rate of change of the valence band edge because they move in parallel with each other, right? But energy levels are directly related to potential. And so dEc by dx and dV by dx, the change of potential across the material, are related to each other by a charge Q, right? And dV by dx is equal to minus the electric field. And so dEc by dx is minus Q times the electric field. And so dN by dx is equal to Q times the electric field dN by dx is equal to Q times the electric field times N over KT. So that's basically what we end up with. And we know that dN by dx times dN is equal to mu n times E. So starting out with this, mu n times the electric field is equal to dN times Q times the electric field times N over KT. Now N is going to cancel with N, and the electric field is going to cancel with the electric field, and this gives us a relationship which is that dN is equal to KT over Q times mu n. Similarly, we can get a relationship for dP and mu p, which is dP is equal to KT over Q times mu p. These are known as Einstein's relationships, and they show that diffusivity and mobility for electrons and holes are essentially the same thing. They're just related through a physical constant, which is KT over Q, which is the thermal energy of the system, because they both represent the same thing, how easy it is for charge to flow through the material.